Okay, starting off. Okay, um, so our project, I'm going to explain on how we use SVM to classify between the two, uh, classify between the space particles. Either it is a gamma or a hadron. So we're using support vector mission approach in for the classification. So terminologies of a SVM, starting off with we have the hyperplane. Hyperplane is represents the line or the hyperplane plane that separates between two classes, separates the given points into different classes. So a hyperplane can also be in higher dimension based. It's a could be also higher dimension margins. Margin is represented as a distance between the hyperplane and the closest data point. A lower, like a larger margin, lower the chances of misclassification in the data point. Key concept in SVM, SVM could be used for uh, a linear SVM and non-linearly separatable SVM. So in case of linear SVM, it's either a straight line, the hyperplane is linear. On non-linear separatable ones, we use different approaches, two main techniques to actually um, achieve that. We use the kernel trick and soft margins. Um, and what are the tuple parameters in an SVM? So we have the C parameter, that is the highest C represents um, highest C represents low classification errors, and a low C focuses on increasing the margin size. Kernel, so you can have different choice for the kernel. It could be linear polynomial or RPF. So then, what are the advantages, pros and cons for an SVM? SVM effective SVMs are effective on very higher dimensional spaces. So the more higher dimensions you have, the more hyperplane and more accurate your classification will be. Versatile, you can use different kernels. That is another advantage. It is robust to overfitting. What are the disadvantages? It's not efficient on very large data set. It's it's very memory intensive and very hard to tune as well. Here in our use case, I'll explain how we are actually using SVM. So we import the model. We have divided the data set into a training set and another set that used for prediction as well. So we have so here the model is trained data set, and we y predicted is calculated based on the test set that we have given, and we have print the report for the test versus predicted. Then three, let's look at the report in very detail. So it breakdown SVM report breakdowns into it breakdowns into two classes. Uh, class zero represents the hadron. Sorry, the gamma. Class one represents the hadron, and you have a precision of 82% on and the hadron class, and sorry, the gamma class, and 89% on the hadron class. Let's look at these three metric. uh, Result metric precision. So precision is a ratio of correctly predicted positive observation to the total number of predicted positive. Recall is a ratio of the correctly predicted positive to the actual positive. So F1 score is the harmonic mean between a precision and a recall. Support support literally means the actual number of data points or actual occurrence of each classes. So here we had around 1,335 samples of gamma and 2,469 cases of hadron. So even you can see in both classes A and one, we have an average accuracy of 87 percentage. Even though the support or the number of data points in each classes, uh, class one is twice twice large that of class 0. That in a nutshell, uh, the approach using SVM. Thanks a lot.